Right, hello everybody, and welcome to the first POP webinar. My name's Jonathan Gibson and I work for NAG, and today I'm going to talk about improving the performance of parallel codes. So give you a quick overview of what I'm going to talk about. I'm going to start by considering the issue of code performance, and then look at how you profile and optimize codes, followed by a live demo of a tool I use, and then I'll look at a few real examples of code improvements. Okay, so I think I'll begin with giving a quick overview of the POP service, because this webinar is provided as part of this, so it's probably a good idea to let you know what it is at the start. So it is a collaborative European project funded by the Horizon 2020 programme, and it runs for 2.5 years, and that's until the end of March next year. And POP stands for Performance Optimisation and Productivity. And the idea is we're funded to provide free services to academia and commercial organisations within Europe. And we look at parallel codes, parallel applications, and we help provide the customers with an understanding of the behavior of those codes. And we do this across a range of application areas, platforms, and scales. And we feed back to the users suggestions and support on how to rewrite their codes in the most productive way. Okay, so the organisation consists of a number of participating institutions. So I've already mentioned I work for NAG in the UK, but there are a number of organisations listed there throughout the EU. And the various members of this team provide expertise in a number of areas. So first of all, performance analysis and optimisation, but we have good knowledge of programming models and practices, and research and development background, so we're used to working in this area. Okay, so that's an introduction to who POP are. So I'll start by asking the question why you might want to improve the performance of your code. Obviously, if you've tuned into this webinar, I expect you already have some interest in that, but I will outline a few important points. First of all, time is money, especially on supercomputers. Time on these machines can be very limited if you're sharing with other users, but also the actual cost of access in terms of the machine itself and the support and the electricity and various other costs tends to be very expensive. So optimizing your time on that machine is obviously a good thing. But also in terms of the science, optimizing the performance for code will allow you to run bigger and/or more complex simulations. And finally, another I think valid point here is you want to remain competitive with similar codes, because the chances are if you have competitors, then they're developing their codes and improving the performance all the time, and you want to at least stay level with that. Okay, so sounds like a good idea, doesn't it? But on the other hand, understanding the performance isn't easy. There's a number of reasons why this is the case. First of all, the codes themselves, and I'm using scientific in a broad sense here, these codes are often very large and developed by many people. So maybe they lack coherency. And for obvious reasons, perhaps, the development of the code is driven by functionality rather than performance. And because of those reasons, I think it's not easy to get an overview of the code's behavior. As well as the codes, I think another factor that makes understanding performance difficult is the machines themselves. The architectures are getting ever more complex. We tend to have many nodes on a system, each consisting of a number of multi-core processors. We have an interconnect connecting those together and a file system. which adds other layers of complexity. At the very low level, we have vector operations to consider and programming to make code vectorizable. And at the memory level, we have very deep memory hierarchies with several levels of cache to consider when writing the code. So I think the upshot of all this is it's not easy to program efficiently. So that begs the question, perhaps, where do we start? Well, I think one of the first things I always look at is, are there any easy wins that can be made? So perhaps the obvious questions to ask are we using the best performing compiler for our code? And the best compiler on a given machine is likely to vary depending on the code. It's not always the same one or the one you expect. Another obvious thing to look at is the choice of compiler flags. Are you getting the optimal performance out of your code through those flags? So look at that. And similarly, are you using the best performing MPI library? So in practice, this means using a vendor MPI library rather than MPI-CH or OpenMPI that you've downloaded from their websites. Okay, but there's only a certain amount you can do before you need to spend a bit more time looking at the code. I think one important consideration before you do is you need to be very selective, I think, before spending time optimizing code. There is quite a well-known quote from Donald Knuth that premature optimization is the root of all evil. Might be a slight exaggeration, but if you look at the full quote and then and look at in a bit more detail what he's getting at there, then it does tell you a lot of important information. And of course, Donald Knuth, for anyone who's not aware, is a well-known figure in the history of computer science, professor at Stanford and the author of The Art of Computer Programming. Okay, so I think the first thing to bear in mind is that the process of optimizing code tends to be time-consuming. And the second factor that people often neglect is that optimized code is often more difficult to read and understand. And the knock-on effect of that is it's more difficult to debug and maintain. So you want to avoid optimizing code unnecessarily. And so one thing to consider, perhaps, to illustrate that, is that if you optimize a routine that only takes 2% of the execution time, that's not going to have much impact on the overall performance of your code. So really, the implication of this is you need a way to understand the behavior of a code in order to guide the optimization process. And this is where profiling and performance analysis come in. Profiling just refers to the monitoring of the code's behavior as it executes. And we'll see in a moment, but there's quite a large number of profiling tools available. And what they do, they help you as the user to answer a number of key questions to guide the optimization process. And I've listed a number of possible questions here. So the first two obvious ones you might want to find out are, what are the most time-consuming routines? And if they're long routines, what are the most time-consuming lines in those routines? In other words, where do you want to focus your attention? But also, is it easy to optimize the code, or is the efficiency already high? Another important question, what needs to be optimized? In other words, what is the bottleneck in the code? It could be efficient use of cache, or is the code being vectorized enough? And in terms of a parallel code, you want to know whether it's load balanced, whether the work's split equally among the processors you have. and that's essential if a code is to scale. And if the code's MPI, it's useful to know how many MPI messages there are and of what size. Okay, so I said there were a number of profiling tools available. So there's a far from exhaustive list. So we'll see examples of some of those as I proceed through the talk. So I won't say anything more about that now. Okay, so I will say something though about the process of profiling and optimizing codes. So this is one way of representing that. You'll see a couple of arrows, a start and a finish. So just get the pointer there. So the start here. So it depends on the tool you're using, but in many cases you first need to instrument the code, and this refers to modification of the executable so that events related to performance get recorded when the code is actually run. And that leads us on to the measurement phase, where you actually run this instrumented code, and that records data for those events. And so after that, you take that data and you present it in various reports using one of the tools. So this could be a different tool to the one used to take the measurements initially. And then this process allows you to, in the next phase, formulate an optimization strategy. It will show you some kind of display showing where time is being spent and where you might want to focus your attention, and you use this information to formulate an optimization strategy and implement optimizations in your code. But you wouldn't assume it's just worked as you would like. So then you need to carry on, you need to record another set of data, analyze and present that data, and then you'll be able to see what improvements have been made and whether you want to continue around this cycle or you're happy to just exit at that point. Okay. Okay, so we'll look at examples in a moment, but I think there's a couple of important factors to consider in this when you're profiling a code that are worth highlighting at this point, I think. So the first one of those is the input data itself. So in practice, profiling results and hence possible bottlenecks in your code are likely to change with different input files. So really, you want to profile a typical production run rather than a trivial test case. So you need to get your input data right. And in terms of the number of cores you run on, in a similar way to input data, the detailed profiling results are likely to change when you run your job on different numbers of cores. This can be useful in the sense of the next bullet point here. So if your code isn't scaling well, you can profile it on different numbers of cores to identify the cause of poor scaling. So you might have a number of subroutines in your code, and you'll see that some of those subroutines are scaling well and others aren't, and that will help identify why your code isn't scaling. But ideally, you want to profile on the number of cores you aim to scale up to when you do production runs of your code. Okay, so let's have a look at an actual example then. So this is a code I'm working on at the moment as part of the POP project, and I've collected data for this particular code running on Archer using the tool X-Tray, and we're going to look at we're going to visualize this data now using a tool called companion tool called Parava. X-ray and Parava are both developed by Barcelona Supercomputing Center, who are one of the partners on the POP project. So before I run the tool on my laptop, we'll have a quick look at this trace produced by Parava. So what's happened here is I've run the code in question for the first 4 time steps of what would be a very long run. Normally you'd run for a lot more time steps, but given that each one is more or less the same, so as not to produce too much data, I've just run for 4 here. And so if you go down the y-axis in this trace, each line represents a different process in this 48 MPI process job. And we have time along the x-axis. So up until about this point, we have an initialization phase within the code, and then we have 1, 2, 3, 4 time steps, and then a shutdown phase. So what the bars actually indicate in this particular example is a given process performing useful computation. So that basically means it's not involved in any communication or I/O. Okay, so I'm showing the reason I'm showing this particular chart in a slide is because it contains a lot of data. So for the live demo, I'm going to focus on just 1 time step. Okay, so I'll do that now. So I'll exit the presentation, and I will start up WX Parava on my own laptop. So I'm going to load a trace. So this is the same code we've just looked at, but in this case it's only run on 24 cores, just to keep the size of the file small for looking at live in a presentation, so it doesn't take too long. Okay, so this is the same trace but for a single time step. And again, we can see we've got the green and the blue color actually just refers to the length of the line. They both indicate useful duration. And as I say, this is focusing on 1 time step, and the black space is where communication is taking place here. So what you can see is actually there's quite a big load balancing problem here, because this particular process here is working for a lot longer than any of the others. So we have processes finishing useful work, don't know, about significantly shorter than the others. So it highlights here a load balancing issue. And one thing we can also do with this trace is we can add the communication lines showing communication between the different processes. So we can see early on in this time step we have quite a lot of communication going on between all the processes, and at the end of the useful work we can see some communication of data between the various processes using MPI point-to-point type communication. So something else we can do with this particular data, instead of displaying useful duration, we could perhaps display MPI, time spent in MPI calls. So if I scroll down instead of up, choose the view, MPI call.config, and yeah, here we have so the red, in fact all the colours, we've got a red and a pink here, so indicate time spent in MPI calls, and I think the red is actually time spent in an MPI wait all call at the end of the iteration. So again, this is illustrating the load balancing problem in this particular code. Okay, right. I think I'll return now to the presentation, which is somewhere. Right. Right. Okay. So I'm going to mention a few more codes that have been looked at. They've all been looked at within the POP project, but I'm using these examples because that's what I'm working in at the moment. So yeah, in fact, these examples have all been done by other partners within the project, actually. So the first example I'll look at is a code called K-Wave from the Brno University of Technology in the Czech Republic, and this is a toolbox for time domain acoustic and ultrasound simulations, written in C++ with MPI and OpenMP, and profiling this code highlighted a load imbalance in the domain decomposition, and we can illustrate that actually by just going onto the next slide. So we have two traces here. These were both produced with Vampire, and the top trace, what we have, 4 MPI ranks shown, and within each of those we have a number of MPI threads. So on this trace, the red shows MPI synchronization, and the light blue is the excuse me, OpenMP synchronization. And the top trace in this case was the initial performance, showing the load imbalance. So you'll see the two outer processes, which are exterior MPI ranks in this decomposition, spend a lot more time in communication than the interior ranks. So this information was used, and instead a periodic domain was used with identical halo zones for each MPI rank, and that's indicated in the bottom Vampire trace, where you can see the communication shows a much better load balance between the different processes, but also is a lot more compact. It's taking up a lot less space on the timeline. Okay, so I'll look at another example quickly. So this is a code called EPW, electron phonon Vanier code, material science code, University of Oxford, and this is a Fortran code parallelized with MPI. And on the right-hand side here, you'll see a trace produced by Tau, and showing a poor load balance. So this is a code being run on Archer, again the national HPC service in the UK, and each of these blocks represents a different node. So you'll see and this is the time taken for a specific subroutine within the code that takes a significant amount of the overall time up. and you can see the load balancing for this routine is quite poor. There's a wide range of time taken. And looking at the routine, it was discovered that this is down to I/O, the time taken writing out to disk. And so the code was modified so that only one rank wrote the output rather than every MPI rank. And that actually led to a 450-fold speed up in the time taken to write the data. And the impact of that was much larger jobs could be simulated. And another example, so this is a smooth particle hydrodynamics code from Stuttgart Media University. So this is a C++ code using OpenMP for parallelism. And again, profiling of this code identified several issues. So profiling here was done with X-ray and Paraver. And that identified a few places where improvement could be made, as listed there. And the developers actually decided to completely rewrite the code based on what they learned, and this led to an overall performance improvement of 5 or 6 times. So quite a significant improvement in this case. And the final example I'll look at is a code from Archon used for the simulation of polycrystalline materials. So profiling was done here using Scholastica, and a number of optimizations as listed were implemented. So you'll see a diagram on this one looking at how the work was distributed to threads before and after. So that led to a better data locality and so better performance. And yeah, the overall application speedup was 2.5 times. So this particular, the work done on this particular code is going to be the subject of a future webinar. So you'll hear about this one in a lot more depth if you tune in for that. Okay, so there's just a few examples to illustrate what can be achieved through profiling and optimization. So we have had a number of questions about the POP service, so I'm just got a couple of slides to answer those first of all, and then I'll address a couple more questions that we've had from attendees of this webinar. So first of all, I mean, a number of people have asked what does POP actually do? So there's basically there's 3 main types of work we do. So if someone gives us a code, then initially we audit that code. So basically we profile it and identify the performance issues in that particular code. This tends to be followed by a performance plan where we identify the cause of those issues and suggest possible fixes. And perhaps the final stage is the proof of concept, where we actually demonstrate those improvements in software. So this is likely to be some kind of standalone app implementing those changes, and this could be a significant amount of effort. So yeah, and another question is who is POP for? So I think obviously code developers, so we can provide assessment of the detailed behavior of a code and suggest productive directions for refactoring it. But equally, it might apply to users and infrastructure operators, so we can assess achieved performance of a code in production conditions, maybe suggest how the environment could be modified, or provide evidence for interaction with the code provider, or perhaps training. And equally, it might apply to vendors in terms of benchmarking customer support and system design. Okay, so yeah, a couple of questions I also noted from the attendees. Someone asked whether you can profile a Python code. Well, I mean, you can. I mean, there has been one of the POP audits was done on a Python code. It's a commercial code, so I can't say what the code was. But it used it was a Python code using MPI and OpenMP, and that was profiled using X-Ray and Parava, which work very well now with Python. So you know, if you're not sure, then ask us, I think, really. And yeah, another question we got in as well, actually. Just have to read this one. Yes, yeah, sorry, couldn't read my own writing for a second. What are the biggest issues in the codes you are seeing? Right, well, I think I don't think there's one main problem that's been identified, but I think in a lot of cases the problem lies in the communication, and that can be made more efficient. And also load balancing, as we've seen in the examples we've looked at, actually is often quite an important issue. But I mean, it does depend very much on the code. It does vary a lot. Okay, right, so that looks like my half an hour is more or less up. So obviously I can't say a great deal in half an hour, so I'll point you to that particular website. So there's a selection of training materials available on the POP website that you can look at your leisure. If you have any questions regarding this webinar or anything about it, then please email pop@nag.co.uk. But if you're actually interested in using the POP service, then email the main POP address, which is at Barcelona Supercomputing Center. As I mentioned before, this is the first in a series of webinars, and we hope that you tune into to future webinars about more specific topics. If there's anything you particularly like to hear about, though, then drop us an email and let us know.